Welcome back to Rhythm and Roots, where we explore the incredible ways our minds work. Today, we're diving into something truly mind-bending and fascinating.
And it's an experience we've all had, that moment when your eyes play tricks on you. We're talking about the captivating world of optical illusions.
That's right. Why do we see things that aren't really there, or things that seem to move? The science behind optical illusions reveals a lot about our brains.
For a long time, illusions were seen as simple mistakes by the eye. But it's far more complex. It's about how our brain interprets visual data.
Fundamentally, optical illusions are about the brain trying to make sense of incomplete or ambiguous information. Our visual system is constantly taking shortcuts.
It uses past experiences and expectations to fill in gaps, creating what it thinks it sees, rather than what's truly there.
Let's break down some common types, starting with literal optical illusions. These are when the image we see is different from the actual object.
Think of a mirage on a hot road where you see water that isn't there, or a magician's trick using cleverly designed props.
The object itself is altered, or light plays a trick on our perception, leading to a misinterpretation by the brain.
Next, we have physiological illusions, which involve the eyes and brain. They happen after excessive stimulation to our eyes or brain.
Like after images, when you stare at a bright color then look away, you see its complementary color due to fatigued photoreceptors.
Or the motion after effect, when you stare at moving patterns. Then stationary objects seem to move in the opposite direction.
These are temporary effects, showing how our sensory organs can get tired and briefly alter our perception of reality.
But perhaps the most intriguing are cognitive illusions. These result from unconscious inferences our brain makes.
They involve our brain's assumptions and attempts to solve what it sees, often based on learned rules about the world.
A classic example is the Müller-Lyer illusion. Two lines of the same length appear different due to arrowheads.
The brain interprets inward-pointing arrowheads as closer corners and outward-pointing ones as farther corners.
So, it adjusts its perception of line length based on that depth cue, even though the lines are objectively identical.
Then there's the Ponzo illusion with converging lines, making parallel objects seem different sizes.
Our brain assumes the converging lines are receding into the distance. So, an object placed higher up appears larger,
even though its retinal image is the same size as one lower down. It's our brain's depth perception playing a trick.
The Ebbinghaus illusion is another great example. A central circle appears larger or smaller depending on surrounding circles.
Our brain uses the context of surrounding objects to judge size, showing how relative comparisons influence perception.
And how about the Necker cube? A simple line drawing that can be seen facing two different ways.
Your brain flips its interpretation, unable to settle on one stable view. It highlights how our brain actively constructs reality.
The Rubens vase illusion also plays with figure ground perception. Is it a vase or two faces in profile?
Our brain struggles to decide which part is the figure and which is the background, constantly switching between interpretations.
These illusions aren't flaws in our vision, they're features. They reveal the complex, automatic processes of our visual system.
Our brains are constantly making educated guesses about the world, based on light, shadow, perspective, and past experiences.
Illusions expose these shortcuts, showing us the brain's best guesses. Sometimes those guesses are delightfully wrong, creating magic.
They teach us that perception isn't a passive recording of reality. It's an active, interpretive process, a constant construction.
Every time we look at an illusion, we're peeking into our own cognitive machinery, understanding a bit more about how we perceive the world.
Now, let's dive into some more intricate examples and their implications. Consider the impossible figures, like the Penrose triangle.
These drawings seem to depict a three-dimensional object, but are actually impossible to construct in reality.
Our brain tries to interpret them as plausible 3D forms, but struggles to reconcile contradictory cues simultaneously.
They force our minds into a loop, constantly trying to resolve the impossibility. It's a wonderful demonstration of how our brain seeks consistency.
Then there are ambiguous illusions, where an image can be seen as two different things, but not at the same time, like the old woman/young woman drawing.
Your brain flips between interpretations, choosing one dominant perception. This reveals the brain's tendency to create a single, coherent reality.
Even when presented with conflicting visual information, it's a testament to our cognitive flexibility, but also its limitations.
We also have distorting illusions, which alter the size, length, or curvature of objects. The cafe wall illusion is a prime example.
Parallel lines appear to be tilted due to the arrangement of bricks and mortar lines. This illusion is thought to involve how our neurons process contrast boundaries.
It highlights how even subtle visual elements can profoundly impact perception, leading to significant distortions in what we see.
And the autokinetic effect, where a stationary light in a dark room appears to move. This happens because, without a frame of reference, our eyes drift.
And the brain interprets these drifts as motion of the light itself. It's a powerful demonstration of how context influences our perception.
Optical illusions are not just fun tricks. They're vital tools in neuroscience. They help researchers understand the mechanisms of visual processing.
By intentionally tricking the brain, scientists can map out how different parts of the visual system work together.
They reveal the underlying assumptions and neural pathways involved in seeing, from basic light detection to complex pattern recognition.
Understanding illusions can even help us design better user interfaces or create more effective visual displays in various fields.
From pilots using flight simulators to surgeons performing delicate operations, optimizing visual input is crucial, and illusions offer insights.
The study of illusions is a continuous journey into the brain's architecture, showing us just how active and creative our perception truly is.
It's a reminder that what we perceive as reality is often a sophisticated construction, built by our brains from sensory data.
Every time you encounter an illusion, you're getting a masterclass in the amazing, often surprising, capabilities of your own mind.
Moreover, understanding illusions helps us appreciate the limitations of our senses. We don't always see the world exactly as it is.
Our brain actively filters and interprets information constantly to create a stable, predictable model of reality.
This means our perception is inherently subjective, shaped by our unique brains, and influenced by our experiences and expectations.
It's why two people can look at the same illusion and see different things, or interpret ambiguous figures in varied ways.
This knowledge has implications beyond just visual trickery. It impacts fields like art, design, and even psychological therapy.
Artists use these principles to create depth and movement in their works. Architects design spaces that influence our perception of size.
Even in our daily lives, our brains are performing these tricks constantly, allowing us to navigate a complex world efficiently.
Optical illusions are truly a window into the wonders of our brain, revealing how it actively creates the world we experience.
Thank you for joining us on Rhythm and Roots today. We hope this journey into optical illusions was as eye-opening for you
as it was for us to explore. Join us next time for more captivating insights
into the hidden wonders of human perception. Until then, keep looking closely, keep questioning,
and enjoy the magic your brain creates. Bye for now.